Hey everyone and welcome back to PrepFusion. So today we'll start a new topic of this electrostatics chapter, that is electric potential. So this is the lecture 4A of electrostatics chapter. So up until now we have learned about charges, we have learned about force due to charge, we have learned about electric field intensity due to different charge distributions, we have learned about flux, Gauss law. Now we'll learn about electric potential. It is another concept that is related with the charges and electric field intensity. Okay, so first of all we have to identify what is the definition of electric potential. Electric potential is relative concept and is measured between 2 points. So electric potential is not absolute potential, that is potential at a point. I cannot exactly say what is the, let's say I have 2 points, right? Let's say I have 2 points AB. What is the potential of B? I cannot exactly say, but relative to A, what will be the potential of B? That will be VAB. I can see that. So potential is a relative quantity. Why? If you remember gravity, right? Gravity. If I have like a mass that is just over the surface of the gravity, I say it has a potential energy of mgh. Remember height h, but potential energy with respect to what? With respect to the earth. So this potential energy is with respect to something. This is not exact absolute potential energy. This is with relative to something, right? So that's the meaning of relative. The potential difference between 2 points is the work required to move a unit charge from one point to another in the presence of an electric field. So what does this potential difference mean actually? What does it mean? It means that if I have a point charge, if I have a unit point charge here, okay, let's say Q, and I'm moving it slowly, I'm taking this charge slowly, moving it slowly, okay, not very fast, slowly I'm taking this to point B. So the amount of work that needed to be done, because I had to apply some force, right, to take this charge from here to here. So just same like this particular phone. So this phone is what basically, if I move this phone from this point to point above me, just some distance, I have to apply some force, I have to do some work, right? So amount of work done from moving a charge from A to B is actually defined as electric potential. Okay, so in terms of energy also I can say, in terms of volts also I will say electric potential. All those we'll learn slowly, don't worry. Don't worry if you are not able to understand any concept during this lecture or during the previous lecture, if it had happened, or next time if it will happen, just go along with the lecture, just ask your doubt in the group, or you just text me, or if you watch the lecture continuously, right, it may so happen in this lecture you have one doubt, but in the next lecture, while watching the next lecture, the doubt automatically gets cleared. So it can also happen, right? So absolute potential at a point is the potential relative to a reference point. So again, this is also with respect to a point, but absolute potential actually is with respect to a reference point where the potential is zero. So reference point, I will tell you where the potential can be zero. We like absolute point is also a relative quantity, but with respect to a reference that is a global reference that everyone chooses. We'll see that. Okay, so what is work done? Work done is calculated as the force applied multiplied by displacement. This we know during our JE days. When a test charge is placed in an electric field E, okay, test charge is placed in this electric field E, the field tends to move the charge in the direction of E. So if it is a positive charge, right, it will tend to move the electric field, it will tend to move the charge in this direction. But to move a charge in the opposite direction, I want to move this charge in the opposite direction, not the direction of field. An external agent must perform work. So I have to by myself perform a work to move this charge in the opposite direction. So another important point you can say, understand with example, is this is the phone, and downward is actually the gravity is working downward, right? So to keep it stationary, I need to apply some force, right, so that the gravitational force and the normal force is stationary, is equal to each other. So my hand is actually doing some work, although the overall work done in this system is zero because this is not moving, but my hand is actually applying some force at the top, right, to make this zero. Now if I move this at the top, I'm moving against the gravitational field. So this object has displaced and I have to apply some force, so I had to work against the gravity to move this object here. So obviously some work needs to be done, some by external agent. In this case, what is the external agent? My hand is the external agent. So I hope you got the example. Now this is the electric field. Electric field is we already know this definition. Electric field is force upon charge, like what I can say, limit as Q naught tending to 0, right? This is the definition of electric field, or force can be defined as Q naught, it is charge into electric field. This we already know. Now I know the force, I know the displacement. Displacement will be some delta x displacement, right? So what is work done? Small work done. So this work done is dW actually. Very minute work done, dW is QE force into displacement delta x. Because what had happened is this, right? This is actually moving in constant speed. Okay, velocity is constant. Velocity is constant. As velocity is constant, okay, hence the force is also constant, which will be equal to the external field, force due to the external field, but in the opposite direction. So currently this speed is constant. What is the force? Force will be mg, okay, by my hand, because this is not accelerating. Just assume that this velocity is constant, right? This is moving up with constant velocity. So force is constant. If force is constant, that is equals to mg, then only the velocity will be constant of that particular object. So that's why here assumption is velocity is constant. That's why the force will be equals to Q times E, that is developed by the external electric field. So this force I am giving, okay, but the magnitude of the force is defined by the external electric field. This much amount of force I need to give by the external agent. The differential work done dW by an external agent in moving a point test charge Q in an external electric field generated by a source charge Q, or line charge lambda, or surface charge sigma, or volume charge rho v from a point A to point B is given as this, okay. And F agent will be equals to what? F agent will be simply equals to opposite direction. So like I forgot to make this direction, sorry, I will just make this again, these directions. Basically if a point charge is, let's say I am moving this from here to here, let's say I am at this point currently. So the force due to the external field is here, okay. Force due to the external field is here, force due to the field. Now the force, what force I have to apply? I have to apply simple opposite force to keep the velocity constant, right? Velocity must be constant, else the charge will deflect away on the right hand side. So I have to apply a opposite force. Direction will be anti-parallel, but the magnitude will be same. This will be F external that I need to apply. F external, or I can say F agent. External agent that I need to apply to make this force 0. So now what is the length vector here? The length vector will be this, right, in this direction. So it will have some theta. So the work done by the external agent will be this F dot dl. This formula we already know. F agent dot dl. These things we already know, right? So important point to note here is that always my F due to external agent and F due to the field, okay, external field will be 0. These two vector sums will be 0, right? So basically F agent will just be in the opposite direction. F agent will be negative of F external field, so that to keep velocity constant. To keep velocity constant, okay. So this is the important point that you should know. Obviously we will derive the electric potential for all this charge distribution, don't worry, okay. So the work done due to the external agent can have many forms. So you have to understand all these forms. Don't get scared by all these forms. If the displacement is opposite to the direction of the force applied by the electric field, the work done by the external agent is positive. So basically this displacement is in this direction and electric field is in this direction. So obviously work done due to the external agent will be positive, because the angle between them will be between 0 to 180, will be between 0 to 90. So I can observe here from here as well, right? So in the first case, the angle will be from theta will be 0 to 90 degree. If the displacement is in the same direction as the force applied by the electric field, the work done by the external agent is negative. Why? My charge is moving in the same direction, but I have to the velocity should be constant, so I have to apply a force here. DL is in this direction, my F agent vector is in this direction. What is the angle? Angle is 180, so it will be negative. Cos 180 is negative, so that's why the work done will be negative. The work done by an external agent is negative of the work done by the field. So like we can derive from this expression, like from here we can understand work done due to the external agent will be F agent dot dl. Now F agent, what I can write from here, I have derived is equals to minus F external into dl. Now what is F external into dl? It is simply work done due to the external agent. That's why work done due to the external agent is the negative of work done due to the field. So these things you should know. You should basically have an idea. No need to mug up, but know conceptually why is this happening. Just hold on. Yeah, so here, right, we can actually, now I know what is F external, I know what is F electric field. What is F electric field? It is simply this, right, E external dot dl. This I have derived from here, right, I know from here. Okay, so I can simply integrate it to find out overall work. So due to small length dl, this will be E F external. If I want to find out overall work done from A to B, point A to B, Q will be constant, charge doesn't change, remember, so it will come out and it will be E external dot dl. So this will be the work done due to the external agent. Now I can obviously find out the work done due to the field, that this will be just the negative of this. Okay, I hope you understood this definitions. Understanding the definitions is enough. Nothing, no need to worry about this. Just try to understand, just try to listen carefully what I am saying. Don't make irrelevant doubts in your brain. Okay, so I am explaining everything very clearly here. The negative of the work done by electrostatic forces when bringing a system of charged particles from infinity to a specific configuration can be expressed as. So if a charged particle is at infinity, okay, infinity means infinite distance from the field. Okay, now if it is from infinite distance from the field, I know generally what I know is electric field is inversely proportional to r square or r something like that. So if r is infinity, it is at infinity, that means their electric field is 0, that means work done will also be there 0. That's why that is taken as reference. So r infinity is taken as reference. Okay, r infinity will be taken as reference. Now the work done against the electrostatic force in assembling a system of charged particles from infinity to a particular configuration, and alternatively it can also be described as the work done by a external force when slowly bringing together a system of charged particles from infinity to a specific configuration. So basically this talks about the absolute potential. So this is also another definition for electric potential. So we talk about if I am bringing a test charge from infinity to the field, so amount of work done that I needed to do is will be the absolute potential at that particular point. So let's say this is infinity and this is some point A. So I have some charge Q. I bring this charge from this infinity to this point A. So the potential of this point A will be proportional to the work done, basically. Work done to move the charge from infinity to A point. Okay, we'll talk about this more later on, don't worry. Let's solve an example problem on this. So this is a question. Calculate the work done in moving a charge of 4 microcoulomb from the origin to the point P through the electric field this. Okay, so what will be the work done basically? So I have told you the formula, right? So what is the formula for work done? Work done dw is basically negative q e dot dl. Okay, this is the formula for work done, if you remember, right? It will be minus because it is due to the external electric field. Now what are the calculate the work done in moving. Okay, yeah, through the electric field. So it will be negative, it will not be positive, it will be negative, right? So here this is the work done due to the agent. Okay, where did it go? Work done due to the agent, right? So what is dl? This is given in Cartesian coordinate system, so I will write everything in Cartesian coordinate system. Dx ax cap plus dy ay cap plus dz ez cap. So what I can do, E dot dl. So what will be the total work done? Work done by the agent will be basically integration minus q will come outside point A to point B. So basically from origin to 2 comma minus 1 comma 4 point P, right? E dot dl. E is what? E is 2x yz Ax cap. So I'll just simply copy this, actually that will be better. So we'll delete dot this thing, right? So I'll take this in the next page, that will be easier. Dot dl vector, right? So this is this vector. So this actually becomes, q is they have given -4, so work done will be -4 micro, and right here 10 raised to power -3 -6 integration. This will be 2xyz dx plus, now they haven't mentioned us any, okay, they have mentioned straight line, right? They have mentioned straight line. So I will convert, okay, straight line, x equals to 2y, z equals to 2x. So I will convert everything into a single variable. I will convert everything into a single variable, that will be better for us. So x equals to 2y, so x is equals to 2y, right? And z equals to 2z. So what I can do, I can replace everything in terms of x. Okay, so y equals to minus x by 2 and z equals to 2x. So my electric field will become what? E vector will become 2x, y is minus x by 2, right? Y is minus x by 2 and z is 2x. Ax cap plus x square plus z. Z is how much? Again 2x. Ay cap plus, then again I have x square into not x square, sorry, yeah, it is x square, right? X square into y. Y is again minus x by 2, right? Y is minus x by 2. A z cap. This will become 2 gets cancelled, minus 2x cube ax cap plus 2x cube ay cap minus x cube by 2 az. So from here we have to also identify dx, dy and dz. So what will be from this particular thing, what will be my dy? Dy will be minus dx by 2 and my dz will be 2 dx. So all this we have to replace yet. So this will be a bit of work, more work done than this work. So what will this be? This, right, will be equals to minus 2x cube, dx will remain as it is, dx plus this is 2x cube and dy is actually minus dx by 2, minus dx by 2 plus, obviously I have to integrate. Now I will just tell you the x limits. X limits is what? 0 to 2, 0 to 2, and this will be minus x cube by 2 into dz is how much? Dz is 2 dx, 2 dx. Okay, so this will be what? This will be this simple thing. So this will be like, if I add all of these up, right, this is minus x cube minus 3x cube and this becomes, this also becomes minus, so all of it becomes actually minus. And at the outside I already had a minus sign. Okay, I forgot, I already had a minus sign as well at the outside, minus q. So this becomes total q into 4x cube dx. So this will become q integration x raised to power 4 by 4 gets cancelled 2. So this is this was how much? Q was how much? 4 microcoulomb, 4 microcoulomb into x raised to power 4, 2 raised to power 4, 16. So this will come out to be 64 microjoules. Okay, this will come out to be 64 microjoules. Okay, so yeah, this is the work done by the field. Answer will be 64 plus 64. Do take a note, because due to the external agent, this is the work done due to the external agent, not due to the electric field. Okay, not due to the electric field. So work done due to the external agent. Okay, so this is the answer for this particular question. Pretty straightforward, pretty simple question. These type of questions can also come. So in summary, for you to compute work done, right, what do you need to find out? Electric potential work done. Identify the problem statement. You have to identify what is E, what is DL, along what curve they have told. So this portion is very important. Right now they have told me along the straight line. Now if your E vector, right, if your E vector is conservative, I hope you know what is conservative. We have learned this in vector algebra. If your E vector is conservative, then it doesn't matter what path I take, I will take the simpler path. Okay, I will take the simpler path. How to compute this? We know, we have studied this very well in vector algebra. Okay, just then minus q times this, and we'll identify the work done by EB or due to the external agent. Okay, E dot dl will be this, and then you compute. This is just a step by step process, and this we already know how to compute. Just you have to identify E vector and dl and identify the path. And if the E vector is conservative, then what is the thing? The thing is that it doesn't depend on the path. It is independent of the path. What I'm speaking, if you're not able to understand, then you have definitely not learned vector algebra from me. You have to understand, you have to learn vector calculus from me. Okay. Now let's solve this question. So a charged particle with a charge of minus 1 microcoulomb is charged along a loop. Sorry for the noise. Let's just hold on for a noise. Just hold on. Yeah, now it is still not gone. Yeah, now it is gone. A charged particle with a charge of minus 1 microcoulomb is carried along a loop in an electric field E. Okay, it is carried along a loop in an electric field E, like this. Okay, what is the work done by external agent for a round trip? What is the work done for each path? Now, important point to note, if the electric field is conservative in nature, then the overall work done in a loop will be 0. There will be no work done. If the electric field is not conservative in nature, then the work done will not be 0. How to check conservative nature? You can take the like E rotational thing, right? You can take the E rotational thing. If the electric field is E rotational, then obviously it is conservative. Now we'll check it if it is conservative or not. Okay, so we'll actually get to a conclusion from this lecture, from this question. So what is the work done by the external agent in the round trip? So what I know is, for the first question, okay, I need to find out the closed loop integration of E dot dl along the curve C, right? Along this particular curve C, correct? And I have to find out the work done. Basically, work done of this loop C will be minus Q times E. Now I know something about this. This is something similar, right? This is if you recall, it is the Stokes theorem. So this I can further write double integration del cross E into ds, right? Del cross E ds vector. If you remember, this del cross E dot ds vector. Now, what do I know about this del cross E? I know electric field is always E rotational. So if electric field is always E rotational, that means what? That means that this del cross E will be 0. And why is this E rotational? Because I have told you, right, it is property of electric field. It will be always radially outward. It doesn't have any rotational direction to it. Okay, so this will be equal to 0. So if it is equal to 0, that means electric field is conservative in nature. And if you want to check, right, you can do the del cross E and check whether this will come out to be 0 or not. It will come out to be 0. Electric field is conservative in nature, and if it is not del cross E is not equal to 0, then that is not the correct expression for electric field. You can do a sanity check as well, whether that field is electric field or not, by checking the curl of that vector. If the curl is 0, then that means it is an electric field, because electric field will always be conservative in nature. It will always be E rotational in nature. Conservative in nature. So what conclusion I'm trying to get here is, it doesn't matter what path I follow. Okay, it doesn't matter if I follow this path or something like this path or something like this path, the work done will be 0. Okay, work done will be 0. For the first part, the answer will be 0. Okay, for the second part, we'll solve obviously. It doesn't matter even if they don't give me path, right? Just give me points. I'll just connect the straight line and I will just compute the work done at those particular points. Okay, so I hope you get the point. Electric field is conservative in nature. This is a great conclusion. Now, can you do this second part homework? This is a homework exercise for you. Pretty simple, just simple line integration. These type of line integration we have done so many times previously. So this is just a normal laborious task. That's it, right? You know everything concept. Just do E dot dl integration minus q. You will be able to do it. Okay, this will I will give you as homework. Okay, so let's learn about the potential difference. Now obviously that's how, if you know if there is a loop, right, that's how that's from where the Kirchhoff's voltage law came. So if I have this circuit and this is the voltage source, if I complete from here, I start and I complete a loop, come back here, the overall work done will be 0. That's why the potential difference is also 0 at basically from the same point. Okay, that's why throughout the whole loop the sum of potentials is 0. Okay, from there the KVL comes. The potential difference between 2 points is the work done per unit charge in moving a charge from one point to another in the presence of an electric field. So this definition we already know. So here I am totally writing. So basically it has to be independent of the charge. That's why it is equals to work done but divided by the test charge. So we actually pick a test charge and move it from point A to point B, and then divide the test magnitude of the test charge by the work required to move the charge from point A to point B by the external agent, and that gives me the potential. So it's same as the electric field. The relation of electric field and force is same as the relation of potential and work done. So whatever electric field is to force, the same analogy is holds for voltage to work done. Both are scalars, right? Both are scalars. So I'm just simply dividing it by Q. That's it. Okay. To make it independent of charge. So it is just, we are using the test charge just as a decoy. Just as a decoy. We are making this charge independent. So that's it. So work done divided by charge is simply the electric potential difference between the 2 points. Okay, so I hope you get the point. Same like we'll just compute the work done, then divide by the charge. That will give me the electric potential difference between 2 points A and B. I know how to compute work done. Now calculating the electric potential is the more simpler task. Just divide it by charge. That's it. To define potential at a point, we must choose a reference where the potential is 0. So generally the reference is chosen where the potential is 0. That is generally it is chosen when the distance r is infinity. Very far away from source. Okay, this reference is typically taken as ground or at infinity. So generally we typically take it at ground because ground has 0 potential, or infinity far away. If the potential E and displacement dl are in the same direction, then potential decreases. Okay, what do I mean by decreases? So if you observe that if I'm moving the charged particle in the same direction, right, then the work done will be negative. That means work done will be negative. That means it is reducing. Okay, it is going more negative. So that's why potential is reducing. Potential will be negative. As work done is negative, potential is negative. Here I will say, I just taught you the previous concept that work done will be negative. Delta W will be negative. Hence potential will be negative. And same for the opposite case. If electric field and dl are in the opposite direction, then work done will be positive. I have told you why work done will be positive. Told you. Okay, go back there. You will understand. As work done is positive, hence my potential will also be positive. Why work done will be positive? If I am moving in the opposite direction of electric field, told you previously. The angle is between 0 to 90. Okay, here the angle between dl and the force vector is external force vector is 180 to 90. Here the angle is 0 degree to 90. Okay, so now we need to compare the electric field with respect to A and B of this particular thing. So like will the potential increase or decrease from A and B? Okay, so I'll do 2 problems and the other problems I will give you as homework. Okay, so let's do this 2 problems. So here if I observe that my DL vector is in this direction, right? DL is in this direction, correct? And what is my external force? External force has to be in the opposite direction of the electric field, right? External force has to be in the opposite direction of the electric field. So external force is in this direction. So what is the angle basically? So angle here I can observe that the theta angle, right? Angle theta will always be greater than 90. From here to here, the theta I can observe theta is always greater than 90. So if theta is always, just hold on, if the force external is, force on due to the external agent will be negative. So if theta is always greater than 90, that means my work done will be negative. Okay, theta greater than 90, cos more than 90 is negative, work done is negative. That means delta V will also be negative. What is delta V? Delta V means final minus initial. So V2 minus or VB minus VA will be negative. Hence VB will be lower than VA. So VA will be at higher potential with respect to B. So I can talk relative to B, or I can say other way around. VA will be at lower potential. Sorry, I told otherwise. VA will be at higher potential with respect to B. VB will be at lower potential with respect to A. I can only talk relative to some other point. I cannot directly say that what is VA. Okay, I cannot directly say. So that is the thing that we need to understand. And okay, for this as well, for this can you do all, for the other ones can you do all of the other are homework to you. Okay, you try to do and find out the relation between VA and VB. So now we'll do few questions. So this is one question. A point charge 1 nanocoulomb. So I will mark it as homework. Okay. A point charge of 1 nanocoulomb is placed in free space. Calculate the potential difference between 2 points located 2 meter and 1 meter away from the charge. So a point charge is placed, okay, it is located in the free space. We have to find out a potential difference between these 2 points. Okay, so how do I find out the potential difference? So I will just draw the picture. You don't need to draw it. Okay, you can directly solve it with mathematics, but I will draw it. So here potential, okay, it is placed in, okay, somewhere in place a point charge of 1 nanocoulomb is placed, and 2 meters away from it a point is there, and 1 meter away from it another point is there. Okay, they can be anywhere, right? They can be anywhere. So this is, let's say this is point A and this is point B. Calculate the potential difference between 2 points located at 2 meter and 1 meter. So this 1 nanocoulomb charge will actually produce an electric field, right? Let's say produce electric field in what direction? In AR cap direction. AR cap direction. So I have to write everything in AR cap direction. What will be the electric field produced due to this charge? E due to a point charge. What is the formula? It is Q upon 4 pi R square into AR cap. This was the formula, if you remember, right? So this will be the okay, epsilon is also there because it was D actually. Epsilon is also there. Okay, so this is the electric field. Now what I can say is, what is, like, I can compute the magnitude, all those things I can do. So I will move a point charge from point A to B. So I need to find out work done, right? So what will be VAB? VAB will be simply WAB divided by the test charge Q naught. Okay, so this will be equals to minus Q naught integration of E dot DL. Okay, along I like, as electric field is E rotational, I can choose any path. Choose any path. Choose any path. Okay, I can choose any path, it doesn't matter. what I will choose is r equals to, I will choose a sphere of r equals to, as everything is in spherical, I will choose spherical coordinates only. So I will choose from r equals to 2 to r equals to 1. I'll choose spheres. I'll choose a spherical path. I have a sphere, and from sphere I'm moving from r equals to 1 to r equals to 2. I can choose any path as E is conservative. Okay, that's the reason I can choose any path, right? So what will be my dl? Dl vector will be simply dr ar cap. All the other components will be 0 basically. I don't care, because the dot product of all the other components will be simply 0. R d theta e theta plus R sin theta d phi a phi so here what we need to do is E dot dl. So this will be what? This will be, so q naught will simply get cancelled. Okay, by q naught also I have here, so q naught will simply get cancelled. So VAB will be simply minus E dot dl minus from point A to point B, that is r equals to 2 to r equals to 1. Electric field is what? Q upon 4 pi epsilon. This is in free space, nothing is mentioned, so I will assume free space. They have mentioned free space. So 4 pi r square, and this will be in the AR cap direction dot dr AR cap. All the other components will be simply 0. Okay, all the other dot products will be simply 0. So this will be minus q upon 4 pi epsilon, and this will be minus 1 will become plus. So this will be 1 by 1 minus 1 by 2. So this will come out to be, q is how much? Q is 1 nano, so 10 raised to power minus 9 divided by this, right? This is actually 9 into 10 raised to power 9. Okay, divided by 2. So this will actually come out to be 4.5 volts. So VAB, the potential difference, will be 4.5 volts. This will be your solution to the question. This is pretty simple question, and just this pointing this, understanding this, that what will be my DL vector, okay, how to integrate this is the most important point. Okay, that's how we can easily solve this. Why? Because I know electric field is conservative in nature. Now let's start with this question. Two electrodes whose cross-sectional area view is shown in the figure are at the same potential. Okay, these two electrodes are at the same potential. The maximum electric field will be at the point which. So these two electrodes are at same potential. So maximum electric field will be where? So this is like they are at same potential. That means these two electric fields are same potential. So what I can say is, if this is positive, let's assume that this has some positive electric field, right? This also has some positive electric field. Now what I can say is, electric field generated, they are at same potential, so they will have same electric field. Correct? They are at same potential, they will have same electric field. So what will happen is, this will generate electric field here, right? This will generate, due to this electric field will be generated in this direction, and due to this electric field will be generated in this direction, right? So at C point, actually the electric field will be minimum, because this particular, due to this surface, let's say this surface S1 and surface S2, the electric field here is opposite and this is opposite, right? So C will be minimum. D also, D I can say this is on this side, but here some electric field is on this side, right? Due to this plus charges, again it is reducing. But at A point, what I can say, both the electric fields, due to this whole thing and due to this whole thing, both are at the left hand side, both are adding up. So obviously I can say maximum electric field will be at A. Okay, so option A will be correct. Here I have two discs. Okay, you can assume this has two discs which are parallel to each other. So electric field will be maximum where? At this point, because due to this positive charges as well. So few questions you have to do individually, right? Due to this positive charges as well, the electric field will come. Due to this charges as well, the electric field will come. Okay, so electric field will be maximum at this particular point. So that was about few questions on electric field. Now we'll solve about potential difference, how to find out the potential difference. Okay, so there are two methods. we know that electric field intensity is a conservative vector field, that we know. So if you have to compute the electric field in loop, it will always be 0. If you have to compute electric field between 2 points, I will choose the curve as the easiest path. Choose any path. Why? Because I know. Why is it conservative? Because I know E vector is E rotational. Okay. That means del cross A is 0. That's why the integration, closed line integration will be 0 simply. Okay. So now we'll solve few questions. So this is the question. Just pause the video, try it out by yourself, then I will solve this. So let's solve this question. We have a 1 microcoulomb charge from point moving a charge from point origin to this end point in the external field this. So what will be the potential difference? So potential difference is what? Potential difference V AB is basically minus of the work done, right? Negative of minus E dot dl from A to B, that is from origin M to, or I can write Mn to N. I can directly use the formula. No need to write like the figures and stuff. We can directly use the formula, right? I will simply use a straight line. Okay, simply use a straight line. So here X, Y, all of them are going like from 0 to 1. So I like whenever you want to choose a straight line, right, in 3D, what you do is you use this formula: x minus x1 divided by x2 minus x1 equals to y minus y1 divided by y2 minus y1 equals to z minus z1 divided by z2 minus z1 should be equals to t, a third parameter t, everything you involve in terms of t, and then you simply solve the integration. So x equals to y equals to z equals to t, and t limits will be from 0 to 1. Okay, so things will become very simple here. So dl is dx dy dz. So this will become, I'll just write this once only, from 0 to 1. Okay, t equals to 0 to 1. For now I will not write the limits. X ax plus y ay plus z az dot dl. Dl is what? Dl is dx ax plus dy ay plus dz az. Okay, so this will be equals to, now x is t, right, and dx dy dz, all of those things are also same, dx dy dz. So everything will be converted into t. So this simply will become 3t dt from 0 to 1. Minus sign is there. Okay, so this will be minus 3 by 2 volts. Okay, this will be your answer, minus 3 by 2. So okay, it doesn't depend on charge, right? You remember, it doesn't depend on charge. It just depends on the points. Okay, it doesn't depend on charge because we are dividing the test charge, so it doesn't depend on that. So minus 3 by 2, that is minus 1.5 volts will be the answer. Okay, so now let's move on to the next question. So this question is also pretty good. So we have the electric field along y-axis is shown in the graph. Okay, electric field along y-axis is shown. So here whatever that is shown, right, it is electric field along y cap direction. Keep this in mind. Assume the electric field to be 0 in other direction. It is 0 in other directions, so electric field is only in the y direction. This is in kilovolt per centimeter. Then potential difference between point P and Q. What will be the potential difference between the point P and Q if I move a test charge from here to here? So what is the formula for VPQ? It is simply minus integration of E dot dl from Q to P. Wait, just hold on a second. VAB, PV. Sorry, this should be from, yeah, P to Q, right? Final is Q and initial is P, right? So P is what? P point is what? P basically is the y-axis, right? P is the y-axis. So P point is actually, if I write here, P is basically 0, 1, 0, and Q is basically 0, 5, 0. This is the actual point, right? Because I'm moving in the y-axis only. All the other points are 0. Okay, so now how will I solve? This should be pretty simple, right? Basically, what I have to do is I have to integrate this. So VPQ will be minus. Only along the y direction, dl I will break down as dx, dy, dz. Only along the y direction I will have the component that is e of as a function of y dy, y going from 0 to 5. Okay, this is the function, right? This is the function. Yeah, here, right, we have to mention the electric field. Actually, this is, let's mention it anything 20, and this is, let's say, this is 40 and this is 20, right? So ey will be what? Ey will be e of y will be a straight line, right, with a negative slope. What is the slope? Slope is dy upon dx, that is 20 by 5, that is 4. The slope is 4 kilovolt per centimeter, okay, into y. Y is in centimeters, right? Y is in centimeters. So, and plus initially when y is 0, it is 40. Okay, this is in kilovolt per centimeter. Fine. So this is correct. So now I can easily solve this. So this will be v. This is minus, right? Negative slope because it is reducing. Okay. Slope. I hope you all know how to find out. All these things have been taught in basics of calculus. So this will be negative. I can take inside. So this will be y equal to 0 to 5. 4y minus 40 dy in kilovolt. Okay, so this will become y square by 2, that is 2y square. So this will be 25, okay, minus 40 into 5, 200. So this will be actually huge. So this will be it's going to 2, yeah, y square into 2. Yeah, y square is there and 2 is also there. So this will be 50, right? This will be 50. So this will come out to be minus 150 kilovolt. Okay, so you can do the integration, all these things you can do. Okay, main point is how to do all this. Integration you can do, right? Simple integration, all these things you can do. Main point is how to write this e dot dl. What is e, what is dl? Dl, like I'm not writing it everywhere, right? Dl is what? Dl is dx ax cap plus dy az cap, ay cap plus dz az cap, right? Okay, I'm not writing it everywhere. So the y component will only be taken because all the other components are 0. So if I take the dot product, all the dx and dz, all of those things will be 0. Okay, so let's do this. Determine the potential at a point P3, 4 for the 3 point charges located at Q1, 5 into this, Q2 this and this. Okay, potential at a point here. So whenever they have mentioned potential at a point, right? So we'll assume r equals to infinity as reference. What do you mean by reference? I know how to find the potential due to a charged particle, that is, it is q upon r square, right? So what I will do, potential, like potential due to point 1, okay, potential due to charge 1 from infinity. So I will come from infinity to this particular point P, okay, to this particular point P. From infinity to P I will come, correct? And this charge is located at 0, 0. So what is the distance between these two charges? The distance between these two charges, right, is 5 for the first case. So magnitude of OP1, the distance is 5 units in the air cap direction. So again I will do the simple integration here. So what will be the electric field? Electric field will be due to the charge 1. I will write here E1 dot dl vector. So it will come out to be simple. Point 1 is 3, 4, right? 3 point is 3, 4, or OP1 is 3, 4, 0, z is 0. They have not mentioned 3D figure. So r will be 5 for this, right? R will be 5, right? Correct, because the distance is 5. So what I can do is, this will be from r equals to infinity to r equals to 5. So this will come out to be q1 by 4 pi epsilon r square. and this dl will just become dr, because dl is equals to tr ar cap, so this will become just dr, and r equals to infinity to r equals to 5. So what will this be? V1 infinity will be, infinity is the reference this time, right? So this will be simply, if I do this, right, q1 divided by 4 pi epsilon r into 5, right? Similarly, you will find v2 infinity, it will be q2 divided by 4 pi epsilon. What is the distance between these 2 points? Now I have to find the distance, right? Distance will be simply 4. Like you can find the r vector. So OP vector is what? OP1 is actually P vector minus O vector, that is 3ax cap plus 4ay cap. That's why the distance came out to be this. Now OP2 will be what? P2 vector minus not O vector, this is like a Q2 vector, right, or position vector of Q2. So this will come out to be 3 will get cancelled, 4 ay cap. Okay, so what will be v2 infinity? Basically the distance, right? What is the distance? Distance is simply magnitude of this OP2 vector, that is 4. So it will be simply 4. So like I will just make this in the next page because this is not symmetrical. So first of all we'll compute OP2, and for this OP2 my v2 infinity will be this. Okay, so Q2 is what? Q2 I will just compute that later on. What is OP3 actually? OP3 is again P3 minus PQ3. So what is PQ3? Q3 is at 0, 4, and this is, okay, so this is not P3, this is P only, right? This thing is P only. This thing is P only, yeah. So this will be simply this is in the ay cap direction, so y cap component will be gone, but only x cap component will be left. So again v3 infinity, the magnitude of OP3 will be what? Will be 3. So v3, all the directions are on the air cap, so finally I get this expression only q3 by 4 pi epsilon into 3. Okay, so I will just add these 3 because like all of these are scalar, right? So overall my potential Vp will be simply due to the potential due to 1 infinity plus potential due to second plus potential due to third. Simple scalar sum. So what will happen here? So q1, q2, q3 are all in 10 raised to power minus 8. So I can take in common 10 raised to power minus 8 and divide by 4 pi epsilon. 4 pi epsilon I can replace with 9 into 10 raised to power 9. So like I will just do this only. What will happen here is 1 by 4 pi epsilon q1 divided by, this was 5, plus q2 divided by, now q2 is with sign, right? You have to place the sign over here, you cannot ignore the sign, that is very important. So q2 divided by 4 plus q3 divided by 3. So this is 9 into 10 raised to power 9, and q1, like everything has 10 raised to power 8 common. And what is q1? q1 is 5 into 10 raised to power 8. So it is 5 divided by 5 plus, now this is plus only, so that's fine, 4 into 10 raised to power 8. So this will be 4 divided by 4. This plus, do keep a note here, this is minus 6. This is minus 6. So you have to write with sign. Okay, you have to write with sign, minus 6 by 3. So all the charges, whatever you write at the end, you have to write it with sign, because sign is not taken care here. Okay, sign you have to take care later on, because all of it is assumed to be positive charges. If it is negative, I write negative charge here. So overall, what will this become? This will simply become 0. So potential at this point will be 0. So this is also a reference point. Okay, this will also come out to be 0. This is also a reference point. Okay, so as it is a scalar, it will simply be a sum of all the potentials. Okay, as written here, as potential is a scalar quantity, it will all be sum, but q, you have to understand that charge with sign, you have to write your q with sign. Okay, you cannot ignore the sign. Yeah, sorry for the interruption, some important call came up. So this is a scalar quantity, and the summation of all of them due to point charges. Okay, multiple charges due to multiple point charges here, right? I should have written multiple point charges will be this. Okay, now distance will change depending where the point charge actually lies. So this will be the case. Now we have to find out electric potential for different charge distributions. So I will find out for point charges, we know what is electric potential formula, that is Q upon 4 pi epsilon naught R. But due to different distributions, just like we derive for electric field intensity, we'll derive for potential as well. Don't worry, potential will be much easier than electric field intensity. So for a point charge, we already know, still I can derive. Okay, for a point charge, if I'm moving from point A to point B, what will be the potential? So potential VAB, how can I write? So I'm moving this, right? So if for a small change, for a small work done, what will be the DL? Let's say I am at this particular point. So the DL vector will be here. Okay, DL vector will be here. So, and where is the electric field? Electric field is in this direction, but I will actually apply force in opposite direction, opposite to the electric field, right? This will be F agent. This is where my electric field will actually work. So this will be my theta basically. This will be my theta. Or electric field is in this direction. I know what is basically my what do you say? Okay, from where I am going, final is B, right? What is my, what do you say? What is my angle? Angle is this theta, right? For electric field, because I know the formula of VAB. What is VAB? VAB is E external dot DL. So D dot DL will be, this will be something positive. Overall, it will come out to be something negative. But it all depends on the charge as well. As electric field is outward. If it was inward, things would have differed here. Okay. So here simply I can break this down into VAB will be equals to simply E external DL cos theta, or the angle between them, or all the simple dot product between them, right? So this I know, this is in the dr cap direction, right? E external is what? It is constant. It is constant. Not constant, sorry. It is basically, if you remember, Q by 4 pi epsilon R square AR cap, in the AR cap direction, outside a sphere, if you remember correctly, right? We derived this previously as well. So this will be simple, right? This I have already derived. Still I will derive. VAB will be integration of Q divided by 4 pi epsilon R square, and DL cap we can again write it as dr AR cap plus R d theta A theta cap plus R sin theta A phi cap d phi. But only dr cap will be remained because all the other components dot product will be 0. So I am going from A to B. Okay, so that is RA, from RA to RB. So the potential difference between 2 points due to a point charge will be simply this, Q upon 4 pi epsilon. If you just integrate this, this will come out to be 1 by RB minus 1 by RA. Okay, this will be the expression for potential difference. Okay, so you have to understand this Q is with sign, because here there is no vector to give me the directions. Q will be with sign. Okay, this thing you have to be careful. Q is with sign. Okay, so like you just integrate, what is integration of 1 by R square minus 1 by R, hence minus is outside, and obviously a minus sign was previously here, so this minus sign is still previously here, so the minus gets cancelled, and simply it is 1 by RP minus 1 by RA. Okay, now what if my like initial point, right, is at infinity, A point is infinity. If RA is at infinity, okay, then my VA VB, the absolute potential with respect to infinity, will be what? It will be basically Q by 4 pi epsilon RB. So hence that's why I told you previously that sometimes we take infinity as reference. Sometimes we take infinity as reference. Okay, so that is what we do. So you have to understand this, right? But do remember Q is with sign. So sometimes we take this infinity as reference. Okay, so now let's do another thing. Let's solve it for the line charge. For a line charge, what type of distribution I will take? I will take E external. E external this time will be something different, right? If you remember correctly, what was E external for a line charge? Try to recall what was the electric field produced due to a line charge. If you recall correctly, it was simply rho s or sigma upon 2 okay, it was 2k lambda by pi, right? 2k lambda by, not pi, sorry, 2k lambda by r. the perpendicular distance, right? 2 pi lambda by r. So here actually the distance changes from row A to row B, right? So this r is actually variable. This r is actually variable, it changes. I can write this in terms of row. And what is the direction? It is arrow cap, right? It's arrow cap. If you remember correctly, this was the expression for electric field due to line charge. That's why I am telling you multiple times that you need to remember this expression. This is actually important. So what will be my VAB? So I will just simply integrate this. Okay. Now I will write DL in cylindrical coordinates. So I have written this multiple times. I will not write this here. I mean, I will not expand the DL. I will directly write, which is minus. This will be from row A to row B. This will be 2k lambda by row arrow cap dot arrow. Okay. What in arrow cap, what do you have? D row, right? Only D row I have, nothing else, only D row. Okay. So this one will become ln, this one will become log actually. So VAB will be 2k lambda is actually lambda by 2 sigma, right? Lambda by 2 sigma. Yeah, it is. Am I correct? Yeah, lambda by 2 pi sigma. I can write this as like this as well. Whatever it suits you. Okay, so I can 2k and lambda. It is uniformly distributed, right? Uniformly distributed. That is what my assumption is. Else it will be very difficult to solve. So it will be 2k lambda by 2k lambda will come outside, and this will be ln of row from row B to row A, because minus sign I have taken inside, right? So this will be row A minus row B. So this will be 2k lambda ln row A by row B. Okay, this will be the basic potential, electric potential due to a line charge. Okay, if I am moving from A point to B. Okay, this is the expression. No need to remember this. Just remember the point charge. Remember, derive from electric field. Just remember the electric field, that's enough, right? It will take you 10 seconds to derive from electric field, right? So if my row A is at infinity, then what will happen? Or sorry, not infinity. If my row A is at 1, then that will be potential, but those are edge cases. We don't need to take care of that. But do remember this lambda, right? This lambda is with sign. Okay, lambda is with sign. Okay, this is, you have to take care of the charge distributions, right? So now let's move on to the next point. One thing is, if we like, this is the expression. If there is some reference, you can compute with respect to the reference as well, right? Now let's do it for the infinite surface charge. Again, for the surface charge, if you remember, it is constant. Infinite surface charge, it is constant, sigma upon 2e. Remember, sigma upon 2e or rho s upon 2e, right? So in this case, my E external was sigma upon 2e. And which direction? Now I will just mark the directions here. Whichever direction you prefer, this will be in the A row cap direction, right? A row cap direction, or if it is in the x coordinate, it's in that direction. So any direction you can choose. So I will choose A row cap direction. Okay, if I choose a cylinder, that will be in the A row cap direction, right? So my VAB is equals to minus sigma upon 2e, and this will be d rho, right? A row gets cancelled, and it doesn't matter whether I'm going from point A to point B. Just the what, this will be, this distance from the surface will be row A, and this distance will be row B, correct? So the potential change will simply be rho A minus rho B. That's it, right? Sigma upon. Don't need to remember this, right? Just know how am I deriving it. Okay. I will take the minus sign inside. So it will be sigma upon 2e epsilon into rho A minus rho B. No need to remember, just understand how am I deriving it. Okay. So this is the question that I am giving you as homework. Try to do this question. Find the potential between points P and Q in the electric field defined in this particular cylindrical coordinate system. Okay. So this question is pretty simple. You can just use this formula of what we learned, and that will be basically it. Basically, you can solve this question pretty easily. Okay. So I'll solve this question in the next lecture. So that's it basically for this lecture. And in the next lecture, we'll learn more things about electric field of more finite charge distributions, and also we'll learn about the equipotential surfaces. Thank you for watching, and I will see you in the next lecture.